So, causal finitism is this metaphysical doctrine defended by Alexander Pruss that denies the metaphysical possibility of ontological dependence upon an infinite amount of causal relator of some causal instance. And that's sufficiently clear? Well, I hope not. As Pruss defends causal finitism, it's really about the denial of a causal history of some sort that involves an infinite amount of causal operations, say, an infinite causal regress or an effect brought about by an infinity of distinct causes. So as stated, the issue really is metaphysical dependence of some effect upon distinct causal origins, for suppose there is some causal history that has some definite origin, as in some initial causal item, and then it evolves into a chain of an actually infinite length. That would not be a violation of causal finitism as Pruss views the matter, for each causal item would only depend upon a finite amount of causal items distinct from itself. Sure, the amount of causal items here is actually infinite, and yet, as far as transitive dependence is concerned, no infinite amount of causal items play a role in determining any causal item as far as this chain goes. So then, an infinite amount of causal items or causal relator or whatever can exist. This is not ruled out by the doctrine as Pruss defends it, but what then in this case are the exact conditions that would violate this version of causal finitism? As Pruss puts it, there are intuitively two ways for this to be violated. A. An infinite number of causes cooperating together to produce a single effect, or B. An infinite causal regress. So if we have an infinite amount of causal items generating some effect, then that effect is of course directly dependent upon an infinite amount of causal items, so that is a clear violation of causal finitism. Then there is an indirect, albeit transitive dependence upon an infinite amount of causal items. But maybe A and B aren't sufficient to rule out this relevant type of causal dependence, for suppose there are infinitely many causal items relevant to the causal history of some causal item, then suppose A doesn't hold. Does it follow that therefore B holds? Well, it seems plausible, but obviously that's not no proof. So let us clearly define what a causal history is, and then let us rule out an infinity of direct causes of some causal item, and then let us see if this implies that there must be an infinite causal regress. And if this is so, we can define this relevant version of causal finitism as the impossibility of the existence of an infinite amount of causal relator contained within the causal history of some causal item. So what are causal relator? Well, we could argue all day about the full implication this term should have, but here let's focus on causal relator as causal items that can be brought about by causal means by other causal items, and that can bring about causal items by means of causation themselves. Since we have, in some sense, defined this term by making use of self-reference, this of course isn't the real definition. But we can maybe agree that there are things that are the way they are because they were causally influenced in some way, and that influence other things so that they end up being the way they are. That's not really controversial, but helpful. But what we really want to focus on is the causal history of some item, so we can construct something like what Pruss calls a causal nexus, a graph that illustrates a causal history of some sort. So in this graph we have these nodes that represent causal relator, and they are connected by arrows that symbolize causal influence of some sort, of some causal relator onto some other. So let us state there is a relation between two nodes, C and D, and such that it holds that C is lesser than D, if and only if there is a finite sequence of arrows that all point in the same direction such that C is connected to D by these arrows. The causal history illustrated by this nexus H is the causal history of the causal item E, so that it holds for any causal item C present within H that is not identical to E, that it is of lesser degree than E. Now, as Pruss puts it, causal finitism can be taken to be a claim that every possible history only has finitely many nodes. Or as one could put it equivalently, causal finitism implies that every causal history involves only finitely many causal relator. That would be a very nice definition, but as usual, one has to prove it. So let us suppose that there are infinitely many nodes, and let us remember the violations of causal finitism. A. An infinite number of causes cooperating together to produce a single effect, or B. An infinite causal regress, which we can translate into a language referencing a causal nexus as A star. H has a node that has arrows pointing to it from infinitely many nodes, or B star. H has an infinite backward sequence where all the Cn are distinct. Surely A star cannot hold, as the case of non-finite direct causal influence can be ruled out, because yes, if there are infinitely many causal relata, we could construct a nexus with some node being connected to infinitely many other nodes. Say we don't allow for it, then does it therefore follow that there must be an infinite regress? Because if it does not follow that there has to be such a regress, we cannot take it as an implication from our initial prohibitions that an infinite amount of causal relata contained by H is forbidden. So what we want to do here is stay faithful to the violations of causal finitism as stated by A and B, and show that they imply that there can only be finitely many causal relata contained within the nexus. The idea is that if we have an infinite amount of causal relata within H, either A or B is instantiated. Now, the easy way to do this is to rule out A, namely that an infinite number of causes cooperating together produce a single effect, and then show that if there are infinitely many causal relata, this necessarily implies that there will be an infinite causal regress. So, once again, a history H of an item has infinitely many nodes if and only if A, it has a node that has arrows pointing to it from infinitely many nodes, or B, it has an infinite backwards sequence where all the Cn are distinct. Let's show that if A doesn't hold, B does, in case that there are infinitely many nodes. First, let us look at a nexus H and come forth with some definitions. So, let's say a path from some node A to some node B is a sequence that contains a certain amount of nodes from x1 to xn, such that A equals x1 and B equals xn, and for each consequent members xn and xn plus 1 there is an arrow pointing towards the latter. Then, let us define the term depth. The depth of some node is the length of the shortest path from the node itself to a final node E, of which H is a causal history. So the least amount of causal operations that separates some node from a final node E defines the causal depth, or just depth of some node. Now, say that an ancestor of a node B is any node A unequal to B from which there is a path to B of strictly decreasing depth. That is a path from A equal to x1 with all the subsequent steps to xn equals B such that the depth of every node decreases with every step. Now if the depth of A equals the depth of B plus 1, then it will hold that A is a parent of B. In other words, every direct predecessor of some node is called its parent. Now, next define the set I of n as the set of all nodes of a certain depth. It holds that each set I of some n has only finitely many elements to it. Why? Because there is only a single final node E that has, by the denial of A, only finitely many arrows pointing to it. So it has only a finite amount of parents, as does every one of its parents itself. So if we only ever add up finite quantities to some finite quantity, we would ever end up with a finite quantity. Now, since there are, at most, only ever finitely more parents than nodes of a certain depth, and the initial single node E has a depth of 0, then, by only adding up finite quantities, each set I of n has only finitely many elements. We can also define the sets L of n and M of n as Ln is the set of all nodes with a depth lesser or equal to some n, and Mn is the set of all nodes with a depth greater or equal to some n, so that Ln is always finite and Mn is always infinite, for there are, of course, by assumption, infinitely many nodes. Now, the union of L and M of some n is of course exhaustive, meaning it includes all the nodes contained by H, infinitely many. So now let us define the set of nodes that have infinitely many ancestors as the set of n. Now, if it holds for every node C unequal to E that C is of lesser degree than E, then for every node there is a path of strictly decreasing depth that ends at E, which implies that every node is an ancestor to E, which in turn implies that E is an element of n, for the amount of nodes is infinite. So n is not the empty set. So now a nice strategy to show that there must exist an infinite regress of causal relata is to show that every member of n, every node that has infinitely many ancestors, has a parent that has infinitely many ancestors as well. For if every node that is in n has a parent that is in n, we can always move back a step and remain in n. This way, we could move indefinitely many steps backwards and never run out of an infinite amount of ancestors, at least one of which is a parent to a current node. So as Pruss writes, I now claim that for any n larger than 0, and any node B that is element of I of n and member of the set n, there is a node A, element of the set I n plus 1, and element of n such that h has an arrow from A to B. So, by assumption, the node B, that is element of I of n, has infinitely many ancestors since it is an element of n. But since A star doesn't hold, and any node has only finitely many arrows pointing to it, it has only finitely many parents. Now, this implies that B has infinitely many ancestors than mn plus 2, and the path towards E of said ancestors must cross in plus 1, where node A is located. So the amount of ancestors of B in mn plus 2 is infinite, and each of these is an ancestor to some parent of B in in plus 1. So if there is, as we've just shown, a parent of B in in plus 1 that has infinitely many ancestors and is therefore an element of n, we have found a node A. We have shown that there is at least one node in in plus 1 that has an arrow that connects it with B of in, and that this node is in n, that is, it has infinitely many ancestors. So what we can do now is the following. We can pick a node C1 as E, as that is the final node of a causal nexus, and then pick some node C2, element of H, for which it holds that C2 is also an element of n, and that C2 is a parent of C1, and then we can repeat the same procedure ad infinitum. But what one apparently needs, according to Pruss and maybe everybody else, to apply this infinite pattern of operations to these causal relata is the axiom of dependent choice. So the axiom of dependent choice states that if we have a relation R in some set S such that for each x element of S there is a y that is also element of S, and x relates via this relation R to y, then there is a countably infinite sequence x1, x2, and so on and so forth, such that every xn relates to xn plus 1 for all n. So what does this mean? It means that if you have some set S for which it holds that for each element x of S there is some other element y of S, so that some relation x to y holds, in other words, if for each element x you can find some other elements so that some given relation holds, then you can choose some initial element x1 by some choice function, then look at each of the elements who stand in just this relation to x, choose one of them, call it x2, and then you look at each element that stands in just this relation to x2, you could choose one of them, x3, and then move on this way ad infinitum. The axiom of dependent choice then demands that this procedure is valid or feasible, and so you end up with a sequence x1, x2, x3, and so on, of which it holds that every xn relates to xn plus 1 via R. The relation we have here within our causal nexus is the parent relation, where for every node C of n there is some node D of n that is a parent of C. In other words, CRD holds. So by the axiom of dependent choice, we can always choose some parent of any node that is in n, and therefore we obtain a countably infinite sequence of nodes which may symbolize the infinite regress we were looking for. So we have proven that if we have a history H of an item that has infinitely many nodes, and the axiom of dependent choice holds, then either A, it has a node that has arrows pointing to it from infinitely many nodes, or B, it has an infinite backwards sequence where all the Cn are distinct. Now this means we can simply state that causal finitism forbids any nexus or causal history of some node or causal relata H that contains infinitely many nodes or causal relata. So we can state CF or causal finitism as the impossibility of the existence of an infinite amount of causal relata contained within the causal history of some causal item, or way simpler, every causal nexus H contains only finitely many nodes.